Hello everyone, welcome to the ninth interaction session of network analysis. I'm your TA Dipanita. So this week Sir has covered the two-port networks, and in this interaction we will be solving a few problems related to two-port network. So what exactly is two-port network? It is any circuit that we have solved until now in which like all the circuit parameters are denoted by this box, which is termed as the black box, and there is this input voltage and current and output voltage and current. This is the output side, this is the input side. So there is voltage V1 in the input and a current I1 is entering this input. So as I was saying, any two-port network is denoted by a certain box which consists of all the impedance parameters that are present in the circuit, and there is this input terminal and the output terminal which is denoted by like voltage source and then current source I1, and the output terminal is the voltage of the output terminal is denoted by V2, and a current I2 is flowing in the output terminal. Now inside this box there might be several combinations of series, parallel, it could be a resistor, inductor or capacitor, anything can be present, but we can solve for the output current or voltage or input current or voltage based on the input parameters that are given. Now how are they related, like the input parameter, how are they related to the output how are the output parameters of the network related to the input is given by several equations in two-port network, one of which is calculating the Z parameter or the impedance parameter. Now the input current or voltage is related to the output current or voltage by certain equations using this impedance of the circuit. So like the input voltage V1 is related to the input current and the output current as Z11 I1 and Z12 I2. So this I1 and I2 are the input current and the output current. The output voltage V2 is related as Z21 I1 and Z22 I2. So these are the two equations of the Z matrix. So the Z matrix will contain this Z11, Z12, Z21 and Z22. So once we know, if we know the source voltage, that is V1, and if we know any of the two currents, we'll be able to calculate V2, or if any other parameters may be known in order to identify what is the net impedance across the load terminal, because this output side is actually where the load will be connected. So in any network, this output terminal, like across this output terminal, whatever the load we have will be connected. If the input parameters are known, we'll be able to calculate like how much current is drawn by this load, etc. So in this type of network, two-port network may be used, because in any this is specifically used in transmission lines or even in small circuits where there might be a combination of series, parallel, resistance, inductance or capacitance, which is not of relevance to us, like the branch parameters of these complicated network is not directly required, but only the output or the input terminal is more or less useful to us, for example in case of transmission lines. So how to calculate this this Z matrix is like we will either excite the input and short circuit the output, or consider like the output like either the current is going to zero or the voltage source is short circuited. So from these two equations we can calculate the four Z parameters. For example, Z11 can be calculated by V1 by I1 with I2 equal to 0. So if we consider in this first equation I2 to be 0, we will get V1 equal to Z11 I1, and V1 by I1 will give the value of Z11. So since this is kind of like the source voltage by the source current, this is known as the source impedance parameter. Similarly, Z12 can be calculated by considering I1 to be equal to 0. So if Z12 is given by V1 by I2, which is the source voltage by the load current, I2 is the output current with I1 equal to 0. So for this particular case, how will we draw the two-port network? So in this case, V1 will be there, the voltage across the input, I1 current will be flowing into the circuit, but the current here I2 will be equal to 0. So whatever the voltage drop is across the end of this network, whatever the network was here, this will be equal to V2, but I2 will be equal to 0. So once we solve a couple of problems, you will be able to understand like what I am talking about. Right now, like the equations that we have, these two equations are of importance to us. Similarly, if we consider the second equation here, so you can calculate Z21 which will be equal to V2 by I1, considering I2 equal to 0, and Z22 similarly will be V2 by I2 with I1 equal to 0. Once we calculate this Z values, we will be able to calculate the Z matrix which is required in case of this two-port network. The other matrices that can be formed are the admittance matrix, the hybrid matrix, and the T parameter matrix, which are known as the ABCD parameters. Now in case of admittance, what is admittance? It is 1 by the impedance. Now once we have this Z matrix, we cannot simply take 1 by Z11, 1 by Z22 to calculate this Y matrix. So how is this Y matrix given? Suppose this is a two-port network. Here it is this is the input side with voltage V1 and current I1, and this is the load current that we may be drawing. So please note that this I2 current direction for these circuits is considered like it is going inside the port, which may not be the real case scenario. In real case scenario, actually we will be drawing a load current into the load. So in that case, what we can consider is, since this is just a convention, we can consider IL equal to minus I2, whatever I2 we are considering right now for the two-port networks. In while calculating the Z matrix, the Y matrix, for convenience, it is taken that I2 and I1 are both entering into the into this box, which is unknown right now. So in case of admittance matrix, since it is admittance, so what we can write is the equations like this: I1, that is current, will be equal to, basically V equal to IR relation will be valid, right? So if we write in terms of current, it will be equal to 1 by, let's consider not resistance, let us consider this is a complex quantity, impedance, V equal to I into Z. So it will be 1 by Z into I, and this 1 by Z is written in terms of admittance, which is Y into, sorry, this is V, Y into V. So in this case, the input and the output current equations are written like this: I1 equal to Y11 V1 plus Y12 V2, and this is Y21 V1, Y22 V2. So in this case, we can calculate like the admittance matrix, which are the Y11, Y12, Y21 and Y22 as Y11 will be equal to I1 by V1 with V2 equal to 0. V2 equal to 0 means the load side has been short circuited. Then similarly Y12 will be equal to I1 by V2 with V1 short circuited. So the source side has been short circuited. The current by voltage, which is the admittance, is given by Y12. Similarly, Y21 will be equal to I2 by V1 with V1 equal to 0, and Y22 will be equal to I2 by V2 with Y22 will be V1 equal to 0. So for Y21 it will be V2 equal to 0, right? So these are the impedance and the admittance matrix. Similarly, since in both these cases, what we can see is it is either expressed in terms of like the voltage of the input and output are written in terms of the input and output current, or the input and output current are written in terms of voltages. But in case of the hybrid parameters, we will represent current and voltage in terms of the either the source current or the load voltage, which is as shown. This is again a two-port network. Inside whatever there is unknown. This is V1, this is I1 current flowing in, this is I2 the load side, and this is V2. So in case of hybrid parameter, the input voltage is written in terms of H11, the input current, and the output voltage. So this is V2, and the output side current I2 is written in terms of H21 I1, which is the input current, and H22 V2, which is the output voltage. So now if you see, like H11 is equal to V1 by I1 with V2 equal to 0. That is, the load side is short circuited and V1 by I1 is given by H11, which is actually the impedance. Now if you consider, sorry, this is H12, not 21. So if you consider H12, it is V1 by V2 with I1 equal to 0. That is, source current is 0. The ratio of the voltage V1, that is the source voltage, by the load voltage V2 is given by H12. So this is actually a dimensionless quantity, and this is known as actually the voltage gain. That is, whatever the voltage we are applying to the input, how the output voltage is getting affected. So this is the voltage gain ratio H12. Now if we want to calculate H21, it is given by I2 by I1 with V2 equal to 0. When the load side voltage is short circuited, the current gain is given by H21, and this is again dimensionless, right? H22 is given by I2 by V2 with I1 equal to 0, that is, source current equal to 0, and the unit of this, since it is current by voltage, it is inverse of impedance, that is admittance. So in this case, you see the four parameters that are here do not just simply say whether it is admittance or impedance. It is a mixture of all of it, like it is a voltage gain, current gain, impedance, and admittance. That is why this is known as the hybrid parameter. In case of the impedance matrix and admittance matrix, all the coefficients Z11, Z22, etc. were either impedance or admittances. Now there is another more realistic representation of this two-port network in case of transmission. So as I was saying at the start, like in case of the output, any load that will be connected across here will actually draw current. So I2 ideally should be in this direction, right? And this will be the load voltage, or V2 in this case we are representing, and the source current is represented by I1 and the source voltage is represented by V1. So this is more realistic scenario in case of transmission line. So this T matrix is represented in terms of ABCD parameter. It is called the sending end voltage V1, which is V1, and the sending end current, which is equal to I1. These are written in terms of this is where the load will be connected. So this is the receiving end voltage and current. So it is written in terms of the receiving end voltage and the receiving end current I2. So this is known as the ABCD parameter, which is given by these two equations. Now, in case like you are considering I2 to be in this particular direction, there will be a negative sign in place of I2. I2 will be replaced by minus I2, and it will be A V2 minus BI2 and C V2 minus DI2. So it depends on which way you are assuming the current, and depending on that the equation will be like that. So again similar to before, this is also like a kind of hybrid parameter where we like suppose A is calculated by V1 by V2 with I2 equal to 0 and so on, like rest of them similarly like we have calculated before, we can also calculate like this. So in this case you see this is actually the voltage gain, then again B will be equal to V1 by I2 with V2 equal to 0, etc. Again C is equal to I1 by V2 with I2 equal to 0. This unit is admittance. This is the admittance value because it is I by V. This is the impedance value. This is dimensionless and known as the voltage gain. Similarly, D is equal to I1 by I2. Again a type of current gain with V2 equal to 0. So in both the cases, these two are actually like all the coefficients A, B, C, D or H1, H2, H21, H22. These are all a mixture of either admittance or like impedance and current gain and voltage gain. So these are more like realistic scenario in case of a transmission network. So whatever the problem we will be solving is actually we will be figuring out these parameters, which it may be hybrid parameter or ABCD parameter or impedance or admittance parameter with the governing equations that are mentioned here. So these are the governing equations here. So in case of admittance it is this, and in case of impedance it is this. So whatever the network will be given here, whatever is there inside this black box, this will be given in the question, and we'll have to figure out these parameters. So like there are certain conditions for this network, like for example to be reciprocal there are certain conditions. For example, in case of if the network is said to be reciprocal, then if Z12 is equal to Z21, the network given here is said to be reciprocal. Similarly, there is another condition which is known as symmetric. Reciprocal network means from the output side, if you look into the network and you remember the reciprocity theorem, which is equal to which is that the sending end voltage by the receiving end current is equal to the receiving end voltage by the sending end current. From this particular relation, this relation comes out. This is when the network is said to be reciprocal, and the network is said to be symmetric if we look from the output side and the input side, the network appears to be same, like that is combination of resistance and or impedance, any other impedance is such that if we look from the output side and the input side, it kind of looks similar. So the proof is already taught by sir. If you have any confusion, you can look into it, or if you have any doubt, you can also ask me in the next class. So in that case, in case of symmetric network, the condition is Z11 will be equal to Z22. In case of admittance, similarly for the reciprocal, if the network is reciprocal, then Y21 is given by Y12, and in case of symmetric, it is given as like Y11 equal to Y12. to 2. In case of hybrid, the derivation of this has already been taught, so if you have any doubt, you can look up into the lectures. In case of hybrid parameters, if the network is reciprocal, it is H21 is equal to minus H12. And in case of symmetric network, H11 into H22 minus H21 into H12 will be equal to 1. This is the condition. And in case of ABCD parameters, reciprocal relation is given by AD minus BC will be equal to 1, and symmetric, if the network is symmetric, A is equal to D. These are the relations. So with this knowledge, we will move forward and solve our first problem. If anyone has any doubt until now, you can ask, or else we'll start moving to the first problem. Anyone has any questions?
No, ma'am.
Okay. So the first problem we have is a network is given as shown here, where there is a 3 ohm resistance now in parallel to a like a current source, which is again a voltage dependent current source. A resistance is of 2 ohm is connected, and I2 is the current at port 2, which is the receiving end, and V2 is the voltage. At the sending end, V1 is the voltage and I1 is the current. We have to calculate H11, all the hybrid parameters. Now for the hybrid parameters, we have the equations like this, which is V1 equal to H11 I1 plus H12 V2, I2 is equal to H21 I1 and H22 V2. So there are two ways we can figure out this the H parameter matrix. One of the way, the first way I'll show is just simply write the equations. Since this is a very small network, we can easily write the equations V1 in terms of I1 and V2, and I2 in terms of V1 and V2. And we can then rearrange the equation in this format and calculate H11 and H12. So I'll just show the first way. So like the first way we can do is, like, let's write V1. So in this network, if you see, so how can V1 be expressed? So V1, this is almost like a voltage source that is connected here, right? So we can write a KVL equation in this particular loop. This node and this node are same. This is all connected to the ground. This entire part is connected to the ground. So what will be the value of V1 if we apply KVL in this particular loop? So V1 will be equal to 3 into I1. So we will move in this direction and come back, right? This entire loop is calculated, so V1 will be equal to 3I1. This is one of the equations. Now, if we are to write V2, so we will apply KVL in this particular loop, right? In this particular loop, which will consider this part and this part. In this loop, we will apply KVL. So so when we apply KVL across this loop, so V2 will be equal to, so we are moving through this 2 ohm resistance, I2 current. So if we apply KCL in this node, so point 2 V1 current is flowing in, I2 current is flowing in, so the net current in this particular branch will be I2 plus 0.2 into V1, right? So the net current that is flowing through this 2 ohm resistor is 2 into I2 plus 0.2 into V1. Is this fine? So this resistance is the only thing that we are
Ma'am,
encountering.
explain one. Ma'am, explain again that point, ma'am.
Okay, okay.
That I2. This
Yes.
V2 is equal to 2 into that step.
Yeah. So let me use a different color. So the net, this point to V1 current is flowing here, I2 current is flowing here. So the net current that will be flowing here is 0.2 V1 plus I2, right? This is the total current that will be flowing in this particular branch,
Yes, ma'am.
right?
Yes.
Right? So when we apply KVL across this particular loop, right? So we are starting from, so let's say we are starting, just hold on. So we have applied KVL and we are moving in this direction. Okay, we are moving in clockwise direction. So through this 2 ohm resistance, this current 0.2 V1 plus I2, this much amount of current is flowing through the 2 ohm resistance, right? So this is I into R. This is the current I and this is R, right? And we are moving in opposite
Yes, ma'am.
direction of the current flow, so it is positive. Then we are entering through the positive terminal of V2. So this is minus V2, this will be equal to 0. This is satisfying the KVL equation. So V2 is equal to 2 into 0.2 V1 plus I2, right? Now from, this is fine, right?
Yes, ma'am. Yes, ma'am.
Yeah. Okay. So this is 0.4 V1 plus 2 I2. Now from equation 1 we can replace the value of V1. So V1 is equal to 3I. So it is 0.4 into 3I1 plus 2I2. Okay. So this is 1.2, 0.4 into 3, this is 1.2 I1 plus 2 I2. This is V2. So V2 can be expressed in terms of I1 and I2. So in order to rearrange and write it in terms of the hybrid equation, what we need is V1 in terms of I1 and V2. So this, in this first equation, suppose this equation 1, we write V1 equal to 3 I1 plus 0 into V2 because V2 is not present. Now this equation we have to write I2 in terms of I1 and V2. So we will take the I2 in the other side. So 2 I2 will remain here. This 1.2 I1 will bring in the other side, 1.2 I1 plus V2. So I2 can be written in terms of, this is 0.6, we are dividing the equation by 0.2 and this is 0.5 V2. So the next equation from this equation 2 is in terms of I2 in terms of I1 and V2. So this is 0.6 I1 and 0.5 V2. So this is exactly similar to the notation that is mentioned here. So what will be equal to, what will be the H11? H11 is 3.
Madam, excuse me, madam.
Yes,
In second equation, I2 is minus zero point 0.6, I1 is missing. 0.6 I1 plus 0.5 is missing.
Ma'am, you,
yes.
you have missed I1, ma'am. There. See, point
Okay,
6
okay, okay,
I1.
okay, okay, okay. I see. Okay, thank you. So yeah. So here the H11 will be 3, H12 is 0 because the coefficient of V2 is 0. Then in I2, the coefficient of I1 is minus zero point 0.6 and the coefficient of V2 is 0.5. So this is H11, this is H12, this is H21, this is H22. Right? So this is one way of solving the equation. So right now, since this is a small circuit, uh, writing the equations was was easy, but we can solve the same circuit by considering the like I'll just show you. Uh, so we will rewrite the equation of the hybrid parameters, that is V1 equal to H11I1 plus H12V2, and I2 will be equal to H11I1 plus H121I1 and H22V2. Now, as I have shown in the start, like V1, so in order to calculate H11, what we can do is, it is V1 by I1 with V2 equal to 0. So from this, if we short circuit the voltage source, we can calculate H11, right? So in this way, like we can individually calculate this H11 and I2 by considering this condition. For example, in this case, how the circuit will look like. So since V2 will be equal to 0, that is, this part of the circuit is short circuited. So this is short circuited, the V2. This 2 ohm resistance is there. This is 0.2 into V1. This is 3. This is I1. And this is I2. So there is a V1 voltage here. So this is 2 ohm resistance. Now, so what is the voltage of V1? V1 is again the voltage across this to the voltage that is ground. Now again V1 is just the voltage drop across this 3 ohm resistor, right? Because the next like this particular node, let us consider this node to be A is connected to the ground. So V1 is just the voltage drop across this 3 ohm resistance. So this is the voltage drop across 3 ohm resistance is 3 into I1, right? And the current is, so V1 is equal to 3I1. So H11 is equal to 3. Is this clear? What
Yes,
I'm
ma'am.
what I'm saying is, without going into the equations, you can just write like this. So H11 is done. So H12 will be equal to V1 by V2 with I1 equal to 0, right? So if so let us first finish off H21. Since we have already drawn the circuit with V2 equal to 0, H21 will be equal to I2 by I1, that is the current gain, with V2 equal to 0. It is the same circuit that is here. V2 is short circuited. What is the ratio of I2 and I1? So just like consider this part. So in this case, this part of the circuit, let me highlight it. So just consider this part of the circuit, okay, with these two parameters. Sorry. This particular node is now short circuited, and instead of like if the current starts flowing here, instead of actually like instead of flowing like once the current, this current source 0.2 V1, when it comes out, instead of going through the like this 2 ohm resistance, it will directly take this path, because current will take the least resistance path, right? Since this is directly short to the current. Earlier it was with V2 voltage, there was a voltage of V2, and hence applying Kirchhoff's law, we calculated the current across this branch. But right now, since this is short circuited, so whatever the current that is coming out here is directly flowing through this path, which has the least resistance or short circuit. So we are assuming that I2 current is flowing into it and 0.2 V1 current is coming out. So what can we say? I2 will be equal to minus 0.2 V1. Is this fine? Is this fine?
Yes, ma'am.
Yeah. And we have already calculated V1 equal to 3 into I1, right?
But madam, excuse me,
Yes.
I2 is equal to 0.2 V1 it will be, no?
So 0.2 V1 current is flowing in this direction, right?
Yes.
And I2 current is flowing in the opposite direction.
Okay, in our
In
convention,
our convention, we have assumed
okay,
I2 current to be in this direction, right?
okay, okay,
So it is
okay.
negative minus 2, and V1 we have calculated. This is the same circuit, that is why I am completing the one in which V2 is equal to 0. So we have calculated V1 is equal to 3I1. So we'll just plot the value of 3I1. So this is minus 0.6 into I1. So H21 can be written as I2 by I1. So if I take the I1 in this side, so this comes out to be minus 0.6, right? So this value H21 is equal to minus 0.6, right? Now the next condition to calculate H22 and H12. So to calculate H12, the ratio is V1 by V2 with I1 equal to 0. So let us redraw the circuit. So the voltage source is here, 0.2 V1. This is the resistance. This is I2. This is V2. Okay. Now, so here I1 is equal to now 0. So whatever the voltage drop across this 3 ohm resistance won't be there because I2 is equal to 0. So whatever the voltage here will be equal to V1, right? Because there is earlier like there was a voltage drop across this 3 ohm resistance because there was current I1 flowing in it. Now this current is equal to 0, so there will be no voltage drop across this 3 ohm resistance. So whatever the voltage drop across these two nodes will be equal to V1. So if we see, V1 is just a short circuit, right? It's just no elements are connected between this particular node A and this particular ground node O. So V1 will be equal to 0, right? Are you getting it? There is
Yes,
no
ma'am.
element
Yes,
connected.
ma'am. Yes, ma'am.
Yeah.
Yes, ma'am.
So V1 is equal to 0, so irrespective of what is there in V2, H12 will be equal to 0. Now H22. H22 will be equal to I2 by V2 with I1 equal to 0. So I1 equal to 0 is exactly the same circuit which I have drawn in here. Now we have to calculate I2 by V2. So we can apply KVL across this particular loop that we have also done before. So if we apply KVL across this loop, okay, this is the 2 ohm resistance. Now since V1 is equal to 0, so 0.2 V1 will also be equal to 0. So there is no current is actually flowing here. There is no current flowing here. So whatever the current I2 is actually flowing across this particular branch, right? So V2 will be equal to 2 into I2 because there are no other
Ma'am,
currents
V1
coming.
is equal to 0. Ma'am, it is I1 is equal to 0, ma'am. How will be V1 is equal to
We
0?
we have assumed I1 equal to 0. Okay.
Yes, yes, ma'am.
So the voltage V1 will be equal to the voltage drop here because there is no
Ah,
voltage drop across 3 ohm resistance because of current going to 0. So
oh,
voltage V1 will be equal to now this particular whatever the node voltage here will be. This is connected to the ground. This is equal to V1. Now
okay,
there
ma'am.
is
Yeah,
nothing
okay.
connected here. It's a short circuit. So V1 is also equal to 0.
Okay, ma'am. Okay.
So this 0.2 V1 will also be equal to 0. So whatever the current I2 is flowing actually will flow through this 2 ohm resistance. So whatever voltage drop we are getting is because of this 2 ohm resistance. So V2 will be equal to 2I2. Right? So we need the ratio between I2 by V2. So I2 by V2 will be equal to half. So H22 will be equal to 0.5. So we get the hybrid parameters matrix as H11 is 3, H21 is equal to minus 0.6, H12 is equal to 0, and H22 equal to 0.5, which is exactly what we have calculated earlier, right? So I'm just showing you two ways of calculating any parameter. Like right now, for example, in this case, we have shown the hybrid parameter calculation. So any Z parameter, admittance parameter, ABCD parameter, etc. can be calculated in this way. You can either write down the equation and then rearrange them in terms of whichever parameter equation that you require, or you can directly look into this equation and apply the conditions to calculate the different parameters. We will, like for simple circuit, we can just use the first process because this is much more simpler. But when the circuit gets more and more complicated, it's best way, because there will be number of equations that will be forming. Suppose if there was another set of parallel and series like connected in after this V2, it would have been difficult to write down all the equations using the first method. So then we will be using this kind of equations. Like the best option is to write these conditions, like either short circuiting the like sending and receiving end side or the sending end side, and calculating the different parameters. So it is totally up to you. Whichever you find easier, you can do it. Is this clear?
Yes, ma'am.
Okay.
Yes, ma'am.
Then let's move to the next question. The next question consists of two-port network that are cascaded one after the another, in which the receiving end, the sending end voltage is V1, and the current that is flowing in, the input current, which is equal to I1. It is going into the first network. In the first network, the output current is I2 and the voltage is V2, which is again the input to the second network. And the second network, the output current is I3 and the voltage is V3. So we are given the voltage and the current equation of the two networks. What we have to do is we have to estimate the Thevenin's voltage as seen from port V3. That is, from this side, what will be the V Thevenin? That is what will be equal to V3, right? V3, assuming like in case of when we calculate the Thevenin's equivalent voltage, we keep all the voltage sources and we calculate whatever the voltage is across the load terminal, or the terminal across which we want to calculate the Thevenin equivalent voltage. So whatever the parameters be here, this V Thevenin is the voltage that we obtain looking from this terminal. Like earlier it used to be the output terminal. In this case, this output terminal is the voltage V3. So if we can calculate V3, we can calculate the Thevenin's equivalent voltage, right? Now in case of two cascaded parameter, like the best option is to use the ABCD parameter. Also, you can see that in the question it is given V1 and I1, that is the sending end voltage and current, in terms of the receiving end voltage and current. So this will give you an intuitive idea that we have to use these ABCD parameters, in which the sending end voltage and current are written in terms of the receiving end voltage and current. Also, like if you have seen sir's lecture, sir has taught like two cascaded ABCD networks, if they are connected, how the net input current or voltage is related to the net output voltage or current. In this case, how V1 and I1 is related to I3 and V3. So in case you have forgotten, I'll just refresh your memory. So this is the V1, this is I1, this is V2, and this is I2. Please note that I2 is in this direction. Earlier we are considering the current in the reverse direction. In ABCD parameters, we consider I in this particular direction, that is coming out of the network, right? So this is written in terms of the ABCD parameters are written like this. Like suppose for this case the ABCD parameters A, B, C and D, sorry, A1, B1, C1 and D1. Let's write this.
Ma'am, this cascaded things are explained in week 11 actually, ma'am. Because
Okay.
week 10 it is not covered, I think.
Okay, I guess, but you have an assignment this time in this
Yes,
cascaded
ma'am.
network. So, okay, then I'll explain it properly, like in case anyone has not really seen the week 11 lecture. It's very simple, like I'll just show you. Suppose this is a network. Let me take a new page, write it there. Just hold on. So, if this is the source voltage or sending end voltage and this is the sending end current, and let this be V2. So I will write all with dash, okay, I1 dash. So this is A dash, B dash, C dash, D dash. These are ABCD parameters, and in case of ABCD, like in case of T network, the current I2 is coming out of the circuit. So the equation to this is written as V1 dash, or the sending end voltage and the sending end current. As we have seen at the start, it is written in terms of A1 V2, like I guess you remember. So these are the equations, okay. These same equations I'm rewriting for the circuit. So A V2 plus B I2, C V2 plus D I2. So these are the receiving end voltages and currents in terms of sending end voltage and current in terms of receiving end voltage and current. This is for the first network. Let for the second network be,
Excuse me, ma'am.
yes,
A, B, C, D should also be dashed.
yes, okay. Now in this case, let this be ABCD. Like in one case I'm using dash, in the other case I won't be using dash. So here this is V1, this is V2, plus minus I1, and this is I2, right? So in this case again, the sending end voltage and the sending end current I'll be writing in terms of the receiving end voltage and current. B I2, C V2 plus D I2. Now imagine these two networks are connected in cascade. So, so this is network 1 and this is network 2. Let's say this is network 2. So network 1 ABCD and this is network 2 A dash, B dash, C dash, D dash. So in this case, in the second network, the current that is coming out is I2 dash and this is plus minus V2 dash, and the input to this is V1 dash and the current that is going is I1 dash, right? This is the second network. For the first network, it is V1 and I1 and the current that is coming out is I2 and this is V2. So just consider this part of the network. So V2 is actually equal to V1 dash. This is V1 dash, right? And I2 is equal to I1 dash, right? If we just consider this part of the network, this is the same current that is flowing into the second network from the first current, and whatever the voltage here, since there are no elements connected across it, so V1 and V2 are actually the same thing, V2 and V1 dash. So using this in the four equations that I have written here, we can write it as, so V2 can be replaced, V1 dash can be replaced by V2, right? So If I rewrite these equations, so it is V2, wait, so I'll better write in terms of matrix. V1 I1 is equal to A, B, C, D into V2 I2, right? And in this case, just hold on. So V1 dash by I1 dash is equal to A dash B dash C dash D dash into V2 dash I2 dash, right? I'm just writing in terms of matrix form. So if I write V1 dash, it will be A into V2 dash plus B into I2 dash, if I like open the matrix. So for the final case, like when two networks are in cascaded, so the voltage, so how I want is like the voltage V1 and I1 in terms of I2 dash and V2 dash, right? So what I want, the equations are in form of V1 and I1, which are the sending end voltage from here, in terms of the final receiving end voltage that are here. So some parameter into V2 dash plus some parameter into I2 dash. Similarly, some parameter into V2 dash and some parameter into I2 dash. This is how the equation I want to be. So since we have the relation which is V2 equal to V1 dash and I2 equal to I1 dash, if I write this particular equation, so let us write, this is the final voltage V1 by I1 equal to A, B, C, D into V2 by I2. Now this V2 by I2, from the relation that I have in here, I can replace V2 by I2 as V1 dash and I1 dash, right? I can replace I2 is equal to I1 dash. So this relation I am going to just replace it and write it here. So in this particular case only, I am just replacing V2 and I2 as V1 dash and I1 dash. V1 dash and I1 dash using this relation. Now we have relation between V1 dash and I1 dash from the second network. So I'll just replace V1 dash I1 dash by, so this AB and CD parameters remain as it is. So V1 dash and an I1 dash I'm replacing from this equation 1. So in place of that I am writing A dash B dash by C dash D dash into V2 dash by I2 dash, right? So basically, so I am writing this at the top. So this V1 by I1 will be equal to the ABCD parameter of the first matrix. I am just replacing this by T. Okay, whatever the transmission line, T represents A, B, C, D, right? And let's T dash represent A dash, B dash, C dash and D dash. These are the, for the two networks, the ABCD parameters of the matrix. So this will be equal to T dash into V2 dash and I2 dash, which is exactly the equation that I want, that is V1 in terms of V2 dash and I2 dash, which are the output of this network. Are you getting this? So basically the input and the output are actually, in case of a cascaded network, it is the multiplication of the ABCD parameters of the two separate networks, which is T and T1 dash. Is this is this clear?
Yes, ma'am, it is clear, ma'am.
Ma'am,
Yes.
Yes, ma'am, it is clear.
ma'am, so we need to calculate separately of two network ABCD parameter.
Yes, if you know the ABCD parameters of the two different networks, then in case of cascaded, the input and the output voltage will be related like this.
Okay,
So,
ma'am.
so we will let us look into this problem. So so let us see. Where did my pen go? Yeah. So in this case, what is the transmission like line parameter T parameter of the first network? Let this be the first network. This is the second network because V1 and I1 are of the first network and V3 I3 of the second network. So in this case, what are the ABCD parameters? Can anyone tell?
5, 8, and 6, 5.
Right. So this is V1 written in terms of V2 and I2, that is the receiving end voltage in terms of the sending end voltage in terms of the receiving end voltage and current. So these are written in terms of ABCD parameters, like ABCD T parameter equations itself. So for the first network, the ABCD parameter are 5, 8, 6 and 5. In case of the second network, it is 5, 7, 6 and 6. So can I write this is the sending end voltage V1 and receiving end current I1. This can be written as T into T prime into, so here in this case if you remember this I2 dash and V2, these are the final receiving end voltage and current. So this is the final receiving end voltage and current, which is V3 in this case and I3. Can I write it like this?
Yes, ma'am. Yes.
Yeah. So let us write the equation. So V1 actually is given in the question as 70. We will later on put it when we are calculating the Thevenin equivalent voltage. So T1 and T1 dash, let's calculate T1 into T1 prime. These two matrix multiplication we'll just have to do. So this is 5, 8, 6, 5 and 5, 7, 6 and 6. So let us just like calculate this matrix. So this is equal to 5 into 5, 25 plus 48. This is 35. So 25, 30 plus 30. Now 35 plus 48 into 42 plus 30. So this comes out to be 25 plus 48 is 73, 83, 60 and 72. So this matrix multiplication gives 73, 83, A, B, C is 60 and D is 72. This is equal to V3 into I3. Now this is like the equations are V1 equal to 73 V3 plus 83 I3. I1 is equal to 60 V3 plus 72 I3. So these are the equations for the ABCD parameter of this cascaded two-port networks. What now first we have to calculate is estimate the Thevenin's voltage as seen from V3.
Excuse
So
me, ma'am.
yes,
Can you explain a little bit about multiplication of these matrices,
okay,
how
okay, okay.
elements?
Yeah, sure.
Thank you.
Just hold on. So, so uh, if this is a matrix, let's say A1, B1, C1, D1, and this is the next matrix A2, B2, C2 and D2. So for when we multiply this matrix, the major rule is like whatever, this is a 2 cross 2 matrix, this is a 2 cross 2 matrix. So this dimension should be equal to this dimension for the matrix multiplication to be valid. If this 2 was 2 and this was 3, this multiplication may not have been possible. These conditions should be satisfied. So whatever the dimension of the second one in the first matrix should be, that is the number of rows in the first matrix should be equal to the number of columns in the first, sorry, I've said the exact opposite thing. So number of columns in the first matrix is equal to number of rows in the first matrix, and the final matrix will be the dimension here. In this case, it is again a 2 cross 2 matrix. So the first row is multiplied by the first column. So it will be A1 into A2 plus A1 into A2 plus B1 into C2. So this is the first element. Then, so first multiplication will be first row and first column. Next it will be first row and the second column. So in this case it will be, so first row and second column, right? So it will be A1 into B2 plus B1 into D2. So if you see in this case what I did was, so 5 into 5, which is 25, plus 8 into 6, 48, right? This is A1 into A2, B1 into C2. This is exactly what we did here. First row multiplied by the first column, then second row multiplied by the second column, then again the second row multiplied by the first column, which is C1 into A2 plus D1 into C2. Then it is the second column, the second row multiplied by the second column. In this case it will be C1 into B2 plus D1 into D2. Is this fine?
Yes, ma'am. Yes, ma'am.
Yeah.
Thank you.
So exactly that we have done it here. So these are the voltage and current equations that we have obtained. So let us take this equation. Wait. So we have been asked to find the Thevenin's equivalent voltage as seen from network 3. Now just consider, suppose this is a network, whatever the network may be, and there will be like suppose, imagine like suppose the network was this, and we were asked to calculate the Thevenin's equivalent voltage across this port AB, right? Or better I'll write, wait. So I'll write it here, okay. Imagine this was the network. Suppose there is a load resistance connected here, and suppose there was a voltage source here, some V, whatever be the resistance, and you were asked to calculate the Thevenin's equivalent voltage AB. So how did you calculate this? We kept the rest of the network intact. This part we had open circuited, right? Because we wanted to calculate the Thevenin's equivalent voltage across this AB terminal, right? So basically there was no current that was flowing here. This particular resistance was actually hanging. There was no current. I equal to 0 was here. We solved the equations for this and we calculated the voltage drop VAB, which is equal to V Thevenin, right? This is how we calculated V Thevenin. In this network 2, what will we do? V Thevenin will be the Thevenin's equivalent voltage as we see from the sending end. So basically it will be the voltage across this port, provided like it should be open, that is I3 right now is equal to 0 because there is nothing connected to V3 terminal, right? So from the first equation, like let me just write this as equation 1 and this as equation 2. What is V3? Considering that I3 will be equal to 0. So if I use the first equation, which is equal to V1 equal to 73 V3, since I3 is equal to 0, this part will be 0. Now in the question, the value of V1 is given, which is equal to 70 volt, which is equal to 73 by V3. So V3 will be equal to 70 by 73, which comes out to be 0.95. 0.9589. So this is V3. Now V3,
Ma'am, can you explain once again, ma'am?
how to so for a general network, like it may be like any network, like there is a series of resistance, whatever the network may be. If we are to calculate the Thevenin's equivalent voltage across this terminal AB, so where basically what we did was we opened this terminal with the load, right? And we calculated the Thevenin's equivalent voltage across this two terminal AB. Whatever the circuit was before, we solved it and we calculated this voltage VAB terminal, right? In order to calculate this V terminal, we had to open up this end of the circuit, right? This load which was before connected, we had to open it. That is, we considered that there was no current because since this was open circuited, there is no current flowing through it. Then we calculated V Thevenin's voltage, and then finally we whatever the resistance, we also calculated the R Thevenin's resistance and across this terminal AB, and then finally we joined with the load in order to get the Thevenin's equivalent circuit. So in this network 2, like this terminal V3, we have to calculate the Thevenin's equivalent voltage. For that, like this part of the network, irrespective of what is there in here, this part of the network where V3 is there, we have to open circuit it. That is, there will be no I3 current that will be drawing because this part of the network is not connected to anything, right? So whatever the Thevenin's equivalent voltage will be equal to V3 provided that I3 equal to 0. In case of sending end voltage, otherwise this V3 is actually kind of
Yes,
the
ma'am. Got it.
voltage that
Got
is
it.
getting measured here. Is it, you got it?
Yes, ma'am. Yes, ma'am.
Okay. So we have to calculate V3 from equation 1 provided that I3 is equal to 0. So from equation 1 we get V1 equal to 73 V3 plus 83 I3. Since I3 is equal to 0, this is equal to 0, and V1 is given in the question as 70. So we get V3, and this V3 is actually the Thevenin's equivalent voltage as seen from port 3, right? Now the second part of the question, in which it is asked estimate the Thevenin's resistance as seen from port 3. So Thevenin's equivalent resistance in normal circuit, how we used to calculate? So whatever the net equivalent resistance across this terminal ABB, that we have to calculate. Or if the networks, suppose remember when we started doing dependent sources, what we did was we calculated the short circuit current ISC. If this was the terminal here, whatever the parameters was here, we calculated this short circuit current and we calculated R Thevenin as V Thevenin by the short circuit current, right? Since the parameter in this ABCD port right now is unknown, what we can do is, for this V3, I'll just take a different color, wait. So across this V3, we will short the terminals and calculate ISC. Okay. Now this ISC is actually the I3 current that is flowing because it is in the same direction, right? So whatever the R Thevenin will be, it will be whatever the V Thevenin voltage we have calculated by ISC. In this case, ISC is equal to I3, right? Is this fine?
Yes, ma'am.
Now note this V3 is actually shorted. This particular Thevenin's equivalent voltage is with the condition that I3 equal to 0. Please note that V Thevenin is not directly equal to V3. V Thevenin is that voltage when the condition exists that I3 equal to 0. Now in case of R Thevenin, it is the Thevenin's equivalent voltage whatever we have calculated by the short circuit current. In this case, short circuit current means the terminal V3 has been short circuited and whatever the current flowing is given by IC, which is in the same direction as I3. So it will be V Thevenin by I3. Now this is a condition when V3 is short circuited, right? So we have to find I3. We have the value of V1. So the best option is using equation 1, which is given by V1 equal to 73. Since V3 is short circuited, the voltage V3 will be equal to 0 plus 83 into I3. This I3 is actually now the short circuit current since terminal 3 has been short circuited. V1 is given as 70. This is equal to 83 into I3 or ISC. So I3 will be equal to 70 by 83, which comes out to be
0.843.
okay, 0.843. So we have the short circuit current. Now we can calculate R Thevenin. So R Thevenin will be equal to 3 by sorry, not 3. What was the Thevenin's voltage? 0.958 by the short circuit current 0.843. So whatever the value comes out is the Thevenin's. Did anyone calculate?
Yes, ma'am. 1.137.
Okay, 1.137. So this is the Thevenin's equivalent voltage. Now the third part of the question is estimate. So we have calculated the Thevenin's equivalent resistance. Estimate the Norton current in the direction as seen from port 3. That is, this is actually basically what ISC is. Because in Norton circuit, we short the terminal and calculate the short circuit current. So this is the answer to the part 3, where I3 equal to ISC or I Norton, which is equal to 0.843 ampere. Is this clear?
Yes, ma'am.
Yes, ma'am.
Okay. Then let's move to the next question.
Sure, ma'am.
So another circuit is given. Earlier we had solved using one dependent current source. Now in this case, this is one dependent voltage source, which is dependent on the sending end voltage or input voltage V1. And the resistance are connected as shown. I1 current is flowing into the circuit. I2 current is also towards the circuit. We have to figure out Z11, Z12, Z21 and Z22. In this case, like since this is a very small circuit, we can just directly write the equations and rearrange them in order to calculate Z11, Z12, right? like in the first problem that I have shown the two ways how to do it, right? So we can move forward with the first approach. So let's so these z parameters, in order to calculate the z parameters, what were the like equation of the z parameters? Z parameters were voltage in terms of the two different currents, that is V1 in terms of I1 and I2, right? So it was Z11 I1 plus Z12 I2, and V2 was Z21 I1 and Z22 I2. So this is how we will rearrange the equation if we simply use like KVL or KCL to write down whatever the circuit conditions are. So in this case, if you see, I1 current is flowing in this way, I2 current is flowing in this way. So the net current that will be flowing is, using KCL, this will be equal to I1 plus I2, right? Both are going into the node, so net current that are coming out of this particular node is I1 plus I2. Is this fine?
Yes, ma'am.
So now we apply KVL in the first loop. So applying KVL in the first loop, it is V1 minus 3I1 minus 3I1 plus I2 will be equal to 0. So V1 will be equal to 6I1 plus 3I2. This is first equation. Now again applying KVL in loop 2. So we apply KVL in loop 2. So it will be equal to V2 minus 2V1. We are encountering this voltage source. Then moving to the 5 ohm resistance, it is minus 5I2, and then encountering this 3 ohm resistance, that is minus 3I1 plus I2. This will be equal to 0. Now we have V1 in terms of I1 and I2, and here we have V1. So we can replace this V1 so that we get the entire equation in terms of V2, I2 and I1, right? So this is V2 minus 2 into V1 is replaced by 6I1 plus 3I2. So it is minus 5I2 minus 3I1 minus 3I2. This will be equal to 0. So V2 is equal to 6 into 2, that is 12I1 plus 6I2, and this is this will be 3I1, and 5 plus 3, 8I2. So 12 plus 3 is 15I1 plus 8 plus 6 is 14I2. So if we compare 1 and 2 with the equations A and B, we can figure out what are Z11, Z12, Z21 and Z22, right? So Z11 is, what is the value of Z11?
6.
Yes. Z12 is 3, Z21 is 15, and Z22 is 14. Is this fine?
Yes, ma'am.
Okay.
Yes, ma'am.
Yes, ma'am.
So just for the sake of it, I'll just show you one value. Like for example, if you want to directly calculate Z11, it would have been, so if I consider equation A, Z11 can be calculated as V1 by I1 with I2 equal to 0. So I2 equal to 0 will imply, so if this was the circuit, this is the circuit. So this is V1, I1 current is flowing. In this case, this I2, this is equal to 0, so there is no current flowing in. So whatever the current that is flowing here will flow through this 3 ohm resistance. This will be again equal to I1 because I2 current is equal to 0. Using KCL, this entire current is flowing through this 3 ohm resistance. So what will be equal to V1? If we apply KVL in this short loop, it is I1 into 3 1 plus I1 into 3 into I1 into 3. So basically V1 will be equal to 6 I1. So V1 by I1 will be equal to 6. So Z11 will be equal to 6, which is again what we got in this case. Similarly, you can at your home, you can just go ahead and apply the other conditions to calculate Z21 and Z22 and all those and verify it. Okay. Is this fine? Then we can move to the fourth question.
Yes, ma'am, we can move.
Yes, ma'am.
Yeah. So in this case, um you have to find out the Z parameter. From there, you have to find out the Y parameter, and you have to comment whether this two-port network is reciprocal and if it is symmetric. So reciprocal and symmetric conditions I have mentioned earlier. Sir has also derived the reciprocal and symmetric condition before. In case you have not seen it, please do. So this is the circuit that is given. So if you see, like in this case, writing the equations for for each of the branches, so there will be multiple KCL equations in this particular three particular nodes, or if you are to write KVL, there will be 3 loops for it, and solving it will be little bit difficult. So what can we do? You have also, I hope you have seen the sir's lecture where sir denotes this T kind of a network. This is like star kind of a network and converts it into a delta network. So this star network can be converted to an equivalent delta network, right? Sir has just mentioned about the star delta conversion. I hope you remember it.
Yes, ma'am. Yes,
Yeah.
ma'am.
Yes, ma'am.
So we will just simplify this network and convert it to a equivalent delta network. So this 8 ohm resistance will be as it is. So this is I2, this is V1 and this is V2. This is I1, this is I2 and this is 8 ohm. So its equivalent star network will be like this. So from this branch, like the branch resistance across this A and B will be RA will be written by, so in case of star to delta conversion, it is R1 R2 plus R2 R3 plus R3 R1 by the branch that is exactly opposite to it. In this case, this is this particular branch. Let this be R3. So it is 3 into 2 plus 6 into 2 plus 3 into 6 by 6. This AB, the resistance across AB will be, right? So 6 plus 12 plus 18 by 6. This is 36 by 6. So this will be equal to 6 ohm, right? So can you calculate the voltage across AC? What will be equal to RAC? What will be RAC? So the numerator will remain as it is, right? It will be 36. It will be multiplication of all the two like combinations of resistance. 36. So what will be the voltage across
18.
Sorry,
Divided by 2. Divided by 2.
divided by 2. So this is
18.
18. And in the third case, BC will be divided by 3, right? So
12.
this is 12. So we this network can be redrawn in a, like, I'll just wait. This network can be just for the ease of our,
Ma'am,
yes.
ma'am, you have any technique to remember these equation because I forget frequently time this conversion.
This, that is what I was like showing you. So the numerator, if we are converting from star to delta, the numerator will be multiplication of the two adjacent resistance. Sorry, not this one. Sorry. In this case, multiplication of two adjacent resistances, right? So this is 3 into 2 into 6 into 2. So this is R1 into R2, R2 into R3, R3 into R4. So I think I had like previously told you this, if you don't remember. So the star connection is kind of like this, right? Let this be R1, R2 and R3. Its equivalent delta will be, so this will be the delta equivalent circuit, right? So what we will, in order to find this R, let's say this is A, B, C. Okay. So in order to find RAB, you will multiply the adjacent resistance, that is R1 into R2 plus R2 into R3 plus R3 into R1. So all the three resistance that are present, R1 and R2, R3, they are multiplied in cyclic order, divided by, since your RAB is in connected across A and B, whatever the opposite resistance will be, which is R3, that will be in the denominator. Are you getting it?
Yes, ma'am.
So you tell me, like across RAC, the numerator will remain as it is, R1, R2 plus R3, R4, R3, R1 plus R2, R3, right? What will be in the denominator? Whoever had doubt, can you please tell me? RAC. AC is,
R1. R1.
right, it will be equal to R1. So you have got the hang of it. Remember just the opposite branch. Okay. So for the ease of our figuring out the circuit, I'm just redrawing the circuit like this. This is 12, this is 6. So this is V2, this is V1, this is I1, this is I2. This is the same circuit, whatever I have got here, this equivalent circuit I am drawing here, because this node B is actually connected to the ground. In this case, this 6 ohm and 12 ohm are actually connected to the ground, right? So I'll take this on a different page. So yeah. So this is the equivalent circuit, right? Now it's easier to write like the equations V1 and I1 in terms of I2 and V2, right? We have to find the Z parameters. So for that we have to write like either we have to figure out the admittance matrix or the impedance matrix, because if we can figure out one, we can figure out the other one, because the admittance matrix will be inverse of the impedance matrix, right? So let us just let us apply. So Let me make this bigger because this is not really evident. So
Excuse me, ma'am.
yes.
We should combine this 8 ohm and 18 ohm so that it becomes simple, madam.
Yeah, we could have like combined like 8. So if we write it, these two are in parallel, so it is like 8 into 18 by 30, how much? 30, 26.
5.538, ma'am.
Yeah. So it comes out to be a complex quantity, so I didn't bother, like recombining them.
Okay, ma'am. Okay.
Okay. So since I1 and I2 are flowing here, so whatever the voltage across this 12 ohm resistance, this will be equal to V2, and whatever the voltage across the 6 ohm resistance will be equal to V1, because you see nothing is connected in between, like and nothing, no other element is present. So V1, if it is the terminal voltage across this is actually whatever the voltage appears across the 6 ohm resistance. Similarly, V2 is the output terminal voltage. Since nothing is connected in between, it is the voltage connected across this 12 ohm resistance, right? And I2 current and IR current are present. And this is like, this is 8 and 18, right? Yeah, 18 and 8. So, if I, so this node voltage is actually V1 and this node voltage is actually V2. Why I can apply KCL now at V1 and V2, right? KCL at V1 if I apply. So I1 current is flowing in, and let in the other 3 branch the current be flowing out. So let current be flowing in this direction, in this direction. So if I apply KCL at V1, I1 will be equal to, so whatever the node voltage is, minus 0. So V1 minus 0 by 6. Then whatever the voltage drop is across this 18 ohm resistance. So it is V1 minus V2 by 18 plus through the 8 ohm resistance. Again, for the 8 ohm, it is connected with V1 and V2. So V1 minus V2 by 18 by 8. This is applying KCL at V1. So I can write I1 in terms of V1 and V2. So this is V1 will be equal to 1 by 6 plus 1 by 18 plus 1 by 8. I did not like remove this parallel connection because again we have to calculate it in fractions, so best option is to calculate all the fraction at the end. That is why I did not remove the simplify it. So again this will be V2 is 1 by 18 plus 1 by 8 into V2. So if I take an LCM, so 18 for 18 it will be 18 into 472. LCM will be 72. So this will be 6 times 12. 18 is not at it. So it is 4 and this is 9. So 12, 21, 25. 25 by 72. And this again will be 72. So for 8 it will be 9 and 18 it will be 4. So I have just taken out the LCM and written in terms of V1 and V2. So this will be equal to 25 by 72 V1 minus 13 by 72 V2. So I1 is written in terms of V1 and V2. So let us just keep it as it is because we can figure out the admittance matrix, because admittance matrix is written as current input and output current in terms of input and output voltage. Now let's apply KVL at V2. Okay, now applying KVL at V2, we get whatever the current is coming here is I2, and let us assume all the other currents are going in this direction, right? So I2 will be equal to the voltage, the current that is flowing through this 12 ohm resistance will be equal to V2 by 12. The current through the 18 ohm resistance will be equal to V2 minus V1 by 18, and the current across 8 ohm resistance will be equal to V2 minus V1 by 8. Again, let us simplify. So in this case it will be minus of 1 by 18 plus 1 by 8 into V1 plus 1 by 12 plus 1 by 8 plus 1 by 18 into V2. So this will come out to be 13 by 72 V1. This will be again LCM if we take, so it will be 18, 12. So again we can take it as 72. So this is 6 plus 9 plus 4. So this is minus 13 by 72 V1 plus this is 15, 19. 19 by 72 V2. So if we look at the admittance matrix equation, it is written as I1 Y11 V1 plus Y12 V2. I2 is written as Y21 V1 plus Y22 V2, right? And the equation 1 and 2 that we got here in terms of I1 and I2, we can compare these two and calculate the admittance matrix, right? Admittance matrix will be, what will be the admittance matrix?
Ma'am, 25.
25 by 72 and
Right.
minus 13 by 72,
Yes.
again minus 13 by 72 and
Yeah.
19 by
So
70.
now you can convert the fraction into you can just put in the values. So it will be 25 by 72 minus 13 by 72, and it is minus 13 by 72 and 19 by 72, right? So if I just put it back, now I can calculate the fractions. So sorry. Because in the question you are asked to calculate both the z parameter and the y parameter, and then you are asked about whether this is symmetric or reciprocal. So first let us calculate the y parameter. This will be equal to 25 by 72. So 25 divided by 72 is 0.4, 0.3472. This will be minus 13 by 72. So it is minus 0.18056. This will be again minus 0.18056, and this will be 19 by 72, 0.2638. This is the Y matrix or the admittance matrix. Now we can calculate. So basically we now have uh, I1 by I2 is equal to Y into V1 by V2, right? V1, V2. Now we need the impedance matrix, which is basically V1 by V2 in terms of Y inverse of admittance matrix inverse into I1 into I2. This is equal to Z, right? Z into I1 into I2. So how can we calculate the impedance matrix? Since we have the admittance matrix, we just have to calculate this Y inverse. That is, we have to find this 25 by 72 minus 13 by 72 minus 13 by 72, 19 by 72, this one inverse. So this inverse is actually 1 by the determinant of this y into adjoint of y, right? So this will be equal to, so the trouble here is just to find the determinant. Once we find the determinant, we can easily get the matrix. So in case of inverse of a 2 cross 2 matrix, it will be 1 by the determinant. Whatever the determinant will be, let us find out. So it will be 25 into 19 by 72 square minus, so this minus 13 into minus 13 will be 13 square by 72 square. This will be the determinant, and in case of finding the adjoint matrix, it is just interchanging A and D parameter, that is 19 by 72 will go here and 25 by 72 will come here, and the sign of C and D will get interchanged. So it will be 13 by 72, 13 by 72. So in case, like, just I'm letting you know, so if we are to find the 2 cross inverse of a 2 cross 2 matrix, what the trick is, the determinant you will have to find out. So it will be 1 by determinant, which is AD in minus BC, and the matrix will be, the adjoint matrix will be, this D will go in A's place, A will come in D's place, C and B will remain as it is with a sign change. This is the trick to find the 2 cross 2 inverse matrix. This is what we have done here.
Ma'am, for 3 cross 3, the trick is different from this.
So it's basically all the trick is the same thing. This is just a shortcut I'm telling. Why? Because in case of adjoint matrix, what do? We remove, for example, if we are to find the first row, the element which is at the first row at the first column, we remove the first row and the first column, and we take minus 1 to the power n plus 1 into whatever the remaining element is. In this case, in case of 3 cross 3, there will be another 2 element here. So it will be that small, the d into whatever the element will be here minus d into whatever the element will be here, and you will have to incorporate the sign in the adjoint matrix. This is just a shortcut I'm telling, like the rule is same for all the matrix inverse. Okay. The cofactor will be like in this case 2 cross 2 matrix, since there are no element, this cofactor will be just D itself, right? In case of the second row second column, it will be minus 1 to the power 2 plus 1. In this case, it will a negative sign will come up, right? And that transpose, so B and C will remain as it is. So in this case, it will be 72 square is in the numerator, so 25 into 19. Let us calculate that. (25 into 19). So it is 475 minus 169. And since all the elements, in all the elements 1 by 72 is there, we can just bring out the 1 by 72. So it will be 19, 13, 13 into and 25. So 172 will go away. So it will be 172 by 475 minus 169 is 306 into 19, 13, 13 and 25. So now you take it all in. This is 306. So you can just calculate it, right? Line 19 into 72 by 306. So it is this comes out to be 4.47. Then it is 13 into 72 by 306. It is 3.058. Again, this side will also be 3.058. And the final one is 25 into 72 by 306, 5.88. So this is just showing you how to calculate Z when Y matrix is given. You just have to take the inverse, the matrix inverse of the admittance matrix. Now, do you remember what is the conditions of being a reciprocal circuit?
Ma'am,
Ma'am, y21 is equal to y12.
Right.
Z12 is equal to Z21.
Yes. So in this case, if you see y12 and y21 are equal, right?
Yes, ma'am.
So y12 will be equal to y21. So this is a reciprocal circuit. But in order to know if it is a symmetric circuit, what should have been the condition?
Y11 is equal to y22 or
Huh.
Z11 is equal to Z22.
Yeah. In this case, y11 is not equal to y22. So this is not symmetric. Right? Similarly, in case of Z, if you see Z11 is Z21 is equal to Z12, but this Z11 is not equal to Z22. So in this case, if the two-port network is reciprocal, yes, it is reciprocal, but is it symmetric? No, it is not symmetric. Right? I hope everyone has got all of it.
Yes,
yes.
ma'am. Yes, ma'am.
Okay. So this is mostly like this is how the problems will be. So just quickly, like as I was telling you, like why to use like the direct formalism. For example, in case of Z11, to find it, we can find it by V1 by I1 with I2 equal to 0. In this type of circuit where there are multiple like branches of series and parallel resistance, writing direct equations will become cumbersome because you will have to write multiple equations. For example, if you are writing KVL, you have to write 3 KVL equations. In place of that, if you simply follow this the parameter determination protocols, you can easily calculate, for example, the parameter Z11, Z12. For example, in this case, I am just asking you to find Z11. So had you written the KCL and KVL equations, it would have been 3 equations, right? Two KCL equations and or 3 KVL equations, right? But in place of that, if I simply use this, like for example, in like always first write down the equations for the for the parameters. For example, V11 equal to Z1 into I1 plus Z12 into I2, V2 equal to Z21 I1 plus Z22 I2. Okay. Now, whichever parameters you were asked, if you are asked to use figure out all the parameters, then you will use all the ways, like first like taking I2 equal to 0, then I1 equal to 0 and figuring out the different Z parameters. In this case, only Z11 is asked, so it can be found out by the ratio V1 and I1 by I2 equal to 0. So when I2 will be equal to 0, so this is I1 and this is I2. Now this I2 is equated to 0, right? So whatever the voltage drop across this 2 ohm resistance is, it is because of the source current, that I1, that is coming up here, right? So if you see this, since I2 is equal to 0, this circuit can be just redrawn like this, right? So this is 5, this is 8, this 6 plus 2 ohm now are in series, right?
No, oh my God, ma'am, answer.
Sorry? Did anyone say anything?
Ma'am, answer will come 9 ohm.
Right, Z11 will be equal to 9. So right now this 6 plus 2 are in series, so this is 8 ohm. So this I1 is getting divided equally among these two branches. So this will be I1 by 2 and this is I1 by 2, right? So V1 can be written by the KVL equation across the first loop itself. So it will be 5I1 plus 8 I1 by 2, that is 5 plus 5 plus 4 I1 or 9 I1. So Z11 is V1 by I1, which is equal to 9, right? In this way, like whenever there is multiple branches, you can just apply these conditions in order to calculate all the parameters, depending on if it is Z11 or hybrid parameters or any of the such case. So we will do one last problem and then wrap it up for today. So in this, for this particular network, you have to find the impedance matrix, that is Z11, Z12, Z21 and Z22. Okay, so how will you do it?
Ma'am, by series parallel operation.
So series parallel as in like will you write different equations, or you will just like first put I1 or I2 equal to 0, like either of the source current to be equal to 0, and calculate it accordingly?
Yes, ma'am.
Yes. So let
Like,
us quickly do it for this one. I2 V2 is equal to Z21 I1 plus Z22 I2, right? So for the first case, when I2 will be equal to 0. So when I2 is equal to 0, this is I2, this is I1. So no current is flowing in this particular branch. No current will actually be flowing in here also. So the circuit actually ends at this terminal, and whatever the voltage across this 1 ohm resistance will be equal to V2, right? So the relation between V1 and I1, since only I1 is the only current that is flowing in the entire circuit, so whatever the equivalent resistance will be across this particular terminal will actually be the ratio of V1 by I1. So Z11 is equal to V1 by I1 with I1 equal to 0, right? And V1 I1 is the resistance across this terminal. Let's say this is AB. So whatever the net equivalent resistance will be, this will be equal to Z11, right? Because there is no other current flowing in it. So if you are to find the equivalent resistance, we can simply start simplifying the circuit. For example, in this case, let us, I won't be writing this 1 ohm resistances at, so this 1 plus 1 plus 1, this 3 ohm resistance is in parallel with this 1 ohm resistance. This is a 3 ohm resistance which are series connected, 1 plus 1 plus 1, which is in parallel with this 1 ohm resistance. So the net resistance now across this terminal, let's say this is CD. So across this CD will be 1 into 3 by 1 plus 3 or 3 by 4. These are all 111 ohm resistance. Now if we re-simplify this circuit, so again there is this 3 series connected resistance, 1 plus 1 plus 3 by 4. So this is 2 plus 3 by 4 or 11 by 4. This is 11 by 4. This is 1 and 1. So the net resistance will be equal to 2 plus 11 by 4. So this comes out to be, sorry, so this 11 ohm resistance is again in parallel with this 1 ohm resistance. So this won't be 11 by 4, this is 11 by 4 into 1 plus 11 by 4 plus 1, which comes out to be 11 4, so 9 15, 4 and 4 will get cancelled, so 11 by 15. So it is 2 plus 11 by 15. So it is 15 to the 30, 41 by 15. So Z11 will be equal to 41 by 15. Is this clear to everybody?
Yes, ma'am.
Similarly, uh, with I2 equal to 0, you can also figure out Z21. Z21 will be equal to V2 by I1. How will you calculate V2? So, since we know the current I1 is flowing across this branch, we can use the current divider rule and calculate the current across each branch. For example, we start doing it from the reverse direction. So, in this terminal I1 current was flowing. If we go back to this particular circuit, in which again this is the source current I1 that is flowing, so whatever the current will get divided among these two circuit will be in the reverse ratio of their resistances, right? So what amount of current will be flowing here? If this is I0, let's say this is I0, what will be the value of I0? So I0 will be in reverse ratio of the current. So reverse ratio means this 1 ohm resistance by 1 plus this total resistance that are there. So 1 plus 3 by 4 times I1. This is using current divided rule, right? So this will be equal to, so 3, 12 plus 3, that is 15. 4 by 15 into I1. So basically I0 is equal to 4 by 15 I1. Now if we go back one step to this circuit, so this was the equivalent circuit up to this much. This CD, you see, towards C, this current was flowing 4 by 15. Now again this current will get divided among this branch and this branch. So let this be I0 dash. So what will be I0 dash? Again in the reverse ratio of their resistance. So in this case there is a 1 ohm resistance, 1 ohm resistance and 1 ohm resistance. So the denominator will be 1 plus 3, and in the numerator, since it is reverse ratio, so it will be 1 times I0. So it will 1 by 4 into 4 by 15 I1. So it is 1 by 15 into I1. So the net current that is flowing in this particular branch is 1 by 15 into I1, right? And so what will be the value of V2? V2 will be equal to 1 into whatever the current that is flowing in that branch, that is I0 dash, which is 1 by 15 into I1. So V2 by I1 equal to 1 by 15, which is equal to Z21. Is this clear?
Yes, ma'am. Yes.
Similarly, you consider I1 equal to 0 and figure out Z12 and Z22. You will, since from this network itself you can see, if you start equating I1 equal to 0 and look from this direction, Z22 will be equal to Z11 and Z12 will be equal to Z21. You will end up with the same values. So the Z
Ma'am,
matrix, yes.
ma'am, in I not why we write 3 by 4? This is equivalent resistance of this circuit.
So if you consider this part of the circuit, wait. So you're talking about this I0 dash, right? Let me use a
Yes,
different color.
ma'am. I not, ma'am, only I not.
Only I0.
Yes, ma'am.
So I0 is equal to, so in this particular circuit, in this particular circuit, this is the branch current which is denoted by I0 here. Okay. So I1 current is flowing into here and it will get divided among this 1 ohm resistance and this 1 plus 1 plus 3 by 4 ohm resistance, right? So the net equivalent resistance across this, let's say this is X and Y. So the net equivalent resistance across X and Y is 1 plus 1 plus 3 by 4, right? So whenever current, like if there is a resistance like this and there is another R2 like this, so this is R2, this is R1, let's say, and one current I is flowing, so whatever the current I naught will flow here will be equal to the reverse ratio of the resistance, that is R1 by R1 plus R2 into I. So if we look at this particular circuit, here R1 equal to 1 and R2 will be equal to 1 plus 1 plus 3 by 4, right? So this is R1, this is R2. So it is R1 by R1 plus R2. Are you able to correlate?
Yes, ma'am. Ma'am, it means we have to reduce up to CD branch this network.
Yeah, I'm just going backwards, like in order to calculate the like using current divided rule, I'm calculating current up to C and D, right? Once I get the current that is flowing across this C and D, then I again go back to the original circuit and again use current divided rule in order to calculate this I naught dash.
Okay, ma'am. Okay, I got it.
Yeah. So we have the Z parameters, which will be equal to, since Z21 and Z12 will be same, so it will be, where is Z11? Z11 is 41 by 15. Z21 will be 1 by 15. So if we look through this terminal and then put current I1 equal to 0, you will see that it is exactly the same circuit and you will end up with this value Z21, Z12, Z21 and Z12 will be equal, and Z11 and Z12 will also be equal. Just do it and verify on your own, like you will be able to do it. It is exactly the same circuit because all the resistance are 1 ohm and they are connected in similar fashion if you look at both the direction. So this particular circuit is both symmetric and reciprocal. Okay?
Yes, ma'am, clear.
So I hope it is clear to everyone. Uh, do you have any specific question? Otherwise, we can wrap it up for today. Okay, then thank you for attending. We'll meet in the next interaction session.